My name is Alastair Rucklidge. I'm from the University of Leeds. I'm a professor in the Department of Applied Mathematics, and I work on nonlinear differential equations. In today's podcast, I'd like to talk about second-order linear homogeneous differential equations. So we'll go through what all those words mean with an example. So let's take, as an example, the differential equation a times y double prime plus b times y prime plus c times y is some function h of x. So y is supposed to be a function of x, and y prime, of course, is a shorthand for dy by dx. That's a second-order differential equation because it involves two derivatives here. Y double prime is d squared y by dx squared. It's linear because there are no things in there like y squared or y times y prime or anything like that. And as I've written it, it's inhomogeneous. That inhomogeneous means y equals 0 is not a solution. Okay, and that's because of this h of x. So what I'm going to be talking about today is the case where h is equal to 0. Now, there's a well-known technique for solving this differential equation, and I could just introduce it to you without giving you any sort of justification for why it works. But what I'd like to do instead is solve the similar problem for a first-order equation, and then you'll see perhaps better the reason for the method that we're going to use. So let's take a first-order linear homogeneous differential equation. So for example, something like y prime plus y equals 0. So that is a first-order equation because it's y prime, no y double primes in there, and it's still linear because there's no products of y with itself or y times y prime, and it's still homogeneous because of that 0 on the right-hand side. And that's an equation we know how to solve. We solve it, well, one way you can do it is bring the y over to the other side. That's y prime equals minus y. We can divide by the y prime over y is equal to minus 1. And now we integrate both sides with respect to x. So that's integral of minus 1 dx on the right-hand side. Now, the y prime is dy by dx. So dy by dx becomes dy, and this integral becomes dy over y is equal to minus x plus a constant. Dy over y, that's an integral we can do. That's logarithm of y. Of course, that's natural logarithm there. And now we can take the exponential of both sides, and you get y is e to the c times e to the minus x. And if we write this e to the c here, well, c is supposed to be an arbitrary constant, so e to the c is another arbitrary constant, so we could call that, say, k, e to the minus x. And what we've shown is this first-order linear equation has a solution of the form any arbitrary number times an exponential. Okay, so now that turns out to be true for second-order equations as well. Solutions of this equation will look like arbitrary numbers times exponentials. The problem is we don't know what those exponentials are. We also don't know what the arbitrary numbers are, but that is a lesser problem. So what we'll do with this equation is we'll look for a solution of the form of an exponential. So we'll look for a solution like y is e to the lambda x, where lambda is a number that at this point we don't know. So if that is going to be a solution of this differential equation up here, well, we better put it in and find the values of lambda that allow this to be a solution of that equation. If we're going to put it in, we need y prime and y double prime. So y prime is the derivative of y. Derivative of e to the lambda x is lambda times e to the lambda x. And y double prime is the derivative of y prime. So we've already got a lambda here. When you differentiate e to the lambda x, it comes down with another lambda, and so you get lambda squared e to the lambda x. Put y double prime in here, y prime in there, and y in there, and we get a lambda squared e to the lambda x plus b lambda e to the lambda x plus c e to the lambda x is equal to 0. We've got a factor, a common factor, e to the lambda x multiplies here each term, so we can write this as a lambda squared plus b lambda plus c times e to the lambda x is 0. What we have now is the product of two things is equal to 0, and that tells you that either one of them is 0 or the other one is 0. And one thing we know about exponentials is they're never equal to 0. So e to the lambda x is never equal to 0, and that must mean that this a lambda squared plus b lambda plus c equals 0. So we've got e to the lambda x is not equal to 0, so a lambda squared plus b lambda plus c equals 0. Okay, so what we said was we're going to look for a solution of the form y is e to the lambda x. And what this is telling us is the values of lambda that will work are the ones that satisfy this equation here. This equation gets a name. Actually, it gets more than one name. It's sometimes called the auxiliary equation, sometimes called the characteristic equation for this differential equation. So it's a quadratic equation, and we can solve it. The solutions, or the roots, are lambda is, and now we just use the quadratic formula, so lambda is minus b plus or minus square root b squared minus 4ac, all divided by 2a. So we've got two roots, one with the plus and one with the minus. Having got those two roots, we say, well, actually, we supposed that we had a solution of this form, e to the lambda x, and what this is telling us is we have two solutions of that form, one with one of the roots and one with the other. So we can actually take both of those solutions together, and our differential equation will have those two solutions. So we'll have lambda 1 and 2 are, lambda 1 is, say, with the plus, and lambda 2 is with the minus. We have two solutions. So we've found two solutions. So y is e to the lambda 1 x, and y is e to the lambda 2 x are both solutions of that equation, provided lambda 1 and lambda 2 are these two numbers. Now, one of the great things about linear equations is if you have a solution, then you can multiply that solution by any number you like, and it will still be a solution. So that means that y is, say, c1 e to the lambda 1x, and y is, say, c2 e to the lambda 2x are also solutions of that equation. So you can see that if you put c1 e to the lambda 1x in here, the c1 comes out as a factor. So c1 here is an arbitrary constant, in the same way that we had that capital K when we solved the first order equation. The other great thing about linear equations is if you've got two solutions, you can add them together, and what you have is also a solution. So what we end up with is the most general solution of this equation is y is the sum of these two things, c1 e to the lambda 1x plus c2 e to the lambda 2x for arbitrary constants c1 and c2. Now, what we actually get in any specific example, of course, will depend on the values of lambda 1 and lambda 2, and those will depend on these numbers a, b, and c. And if you remember the equation that I've just erased, lambda 1 and 2 were minus b plus or minus square root b squared minus 4ac, all divided by 2a. So what we get depends crucially on whether that number inside the square root is positive, or if it's 0, or if it's negative. If it's positive, then the square root is real, and what we'll end up with is two real values of lambda. If it's 0, then the plus or minus doesn't do anything because that number is absent. And the value of lambda that we get is real, but there's only one value. And so we don't have the two solutions that we talked about here. And the third possibility is this number here inside the square root is negative, in which case you take a square root, you get an imaginary number. And so lambda will in general be a complex number. And we're ending up dealing with complex exponentials. So what I'd like to do now is go through an example from each of those three cases.